Uh, Good morning, all. So, in the hello, I'm audible.
Yes, sir.
Yes,
Uh,
sir, you're audible.
Thank you. So, yesterday we started the discussion on the utilization of operational amplifier, that is op-amp, for the design of voltmeter, and we'll see also that we can use the same thing for emitter design as well. So, in the previous lecture, we were talking about application of the non-inverting configuration of the op-amp, which is basically utilized for measurement of low voltages. So that feature is not available with PMMC instrument. The reason being that there is some minimum voltage that is required to drive the meter, because it is an electromechanical instrument. That extra power is not associated available in the case of the passive instrument, which is the PMMC instrument. However, in the case of op-amp, we have an external power supply to provide that extra power to drive, even though the voltage that is being measured is of a low magnitude, right? So here, as you can see, the magnitude which is maximum is that is being measured is 0 to 20 millivolts. Okay, and in the non-inverting configuration yesterday, we have found out that the output voltage is equal to E times 1 plus R4 by R3. Right? This is what we had calculated yesterday. Now it will be interesting to see that how to choose these values. Now what you are given is the meter configure meter specifications, that is its resistance is 10 kilo ohm, and the meter current maximum full scale deflection current is 100 microampere. Okay, now in that case, what will be the output voltage when maximum current is flowing through this? What will be the output voltage at this node? V0, what is V0 in that case when
Sir,
Rm is
Imax times RM.
so what will be that output voltage? I FSD, V0 FSD, Im into Rm. How much is that? How much is that?
So really 1 volt.
1 volt. Right, now you see the voltage that is driving the meter is 1 volt, corresponding to 20 millivolts of the input voltage. Right, now in that case, what is the gain of the amplifier? How
50.
much is the gain? Yeah, so the 1 plus R4 by R3 term is 50. 50, yeah, 50. Right, now one of the resistances you need to choose. Right, so how are you going to choose this resistance? Because neither R3 is given, R4 is given, but an extra information is also given, that is the base current, bias current, sorry, associated with the negative input terminal of op-amp, which is given as 0.2 microampere, sorry, 0.2 microampere. Now, what is the basic condition is that ideally it should have been 0, but it is very low in comparison to what? In comparison to the current which is flowing through these resistances. Okay, so if I assume, or let's say if I take the fact into consideration that R4 is much greater than IB, then I can say that same R4 flows through resistance R3. Okay, although it is basically in fact it is IB, so I4 minus IB. It is true, but since this is the fact which we know that the bias current is very low in comparison to the current flowing through these resistances, we can treat it practically that the current flowing through R3 is also I4. Okay, so how much is I4? I can take say I4 is like 1000 times more than IB. If I take that value, let's say, and I4 is already given, IB is already given, so I4 is 0.2 milliampere. Okay, so if I consider I4 being 0.2 milliampere, then I know that R3 plus R4 is V0 by R4, right? So how much is that? V0 is we have
5,000.
already calculated.
5,000 ohm.
So it is 5 kilo ohms, right? Now you have got two relationship, that is R3 plus R4, sorry, R3 plus R4 is 50 kilo ohm,
Sir,
and
5 kilo ohm. Sir, 5 kilo ohm.
oh sorry, 5, 5 kilo ohm, and 1 plus R3 by R4 is 50. Now you have got two equations. Now you can solve for R3 and R4, right? Initially,
Yes,
we did not have any information, extra information, because we have two unknowns. We should have two equations. So that was not possible. But then we used the fact that IB is very much less than I4 and consider the engineering approximation that the current flowing through R3 is also equal to I4. Okay. So in that way, we can design the circuit components associated with op-amp based voltmeter. Now you can see that in this configuration, we actually amplified the voltage, and that amplified voltage is provided as an input to the metering circuit, this part. So instead of that, noting the fact that the the meter deflection basically is proportional to the meter current, one can easily replace the feedback resistance with the meter itself. Okay. In fact, this is also a non-inverting configuration. The only confusion fact is that we have shown the meter symbol, but it is actually this only. So this is the meter resistance, and this is the resistance R3. Okay, and this is my voltage E, which I'm trying to measure. So we know that what is the output voltage. We can calculate it, right? But what we want is we are interested in measuring E in terms of the current flowing through the meter. In terms of current flowing through the meter. Now we know that the op-amp will always try to maintain this. V plus is equal to V minus. So what is V plus in this case is E. So V minus should also be E. That is the voltage we are measuring. So this node is also at potential E with respect to, hello?
yes, you audible.
Yeah. So this node is also at potential E, right, with respect to the common terminal. And you see this, the current flowing through resistance R3 is E by R3, right? E by R3. And again, noting the fact that the bias current IB is very low in comparison to IM, that is the meter current, then we utilize the fact that IM is equal to IR3, which is E divided by R3. E is the applied voltage. Okay. Now, since same current is flowing, I can calibrate the meter in terms of the current flowing through R3. That means, again, let's take an example that I'm interested in measuring 0 to 1 volts. Okay, so E max is 1 volts. So that means EFI full scale deflection voltage is 1 volt, and the corresponding IFSD is 1 milliampere. Okay, 1 milliampere. And since this IFSD, that is a meter current, is flowing through R3, I know that my R3 will be equal to EFSD divided by IFSD. How much is that? 1 kilo. Right. Once I fix this as 1 kilo ohm, then you can calculate the current, voltage in terms of the current flowing through this. That means if my E becomes EFSD by 2, then how much is the current flowing through the meter? What will be the current flowing through the meter in that case? EFSD by 2 means 0.5 volts. When applied voltage is 0.5 volts, I have fixed this as 1 kilo ohm. What will be the current flowing through the meter?
0.5 milliampere.
0.5 milliampere, right? Which is expected because IFSD is 1 milliampere. When this is half, though this is also will be halved, right? So it is as simple as that. But what will be the output voltage of the op amp?
1.5 volt.
1.5
volt.
volts, because it is Im into Rm plus R3. That is how we have to calculate, right? So this voltage now doesn't matter to us, basically, you see. So the meter current is supplied by the op amp. Okay, that extra current that is being supplied. Okay, so the same electronic voltmeter, whatever we are designed right till now, can be utilized for resistance measurement as well. So this is the one of the configuration of resistance measurement, that is ohm meter, a series type ohm meter, where you connect multiple known resistances, known and precise resistances, in order to measure the resistance of different ranges. So like at these two terminals, you connect the unknown resistance Rx, which is connected, basically getting connected in series with this one of the known resistances based on the switch position, and a constant supply of 1.5 volts. Okay, so it is, so if I simplify this, this is simply as like this for one of the switch positions. So this is my Rx. So we are measuring the voltage using the electronic voltmeter. And what is the range? 1.4 volt range voltmeter. So this is one of the series resistance. So this is 1.5 volts. So as you can see that, if you remember our discussion on resistance measurement also previously, that in order to do the calibration of the meter, the voltmeter in terms of ohm meter, in terms of resistance, we have to have two readings. One is by connecting these two terminals or shorting these two terminals together, corresponding to Rx is equal to 0 ohms. The output voltage will be 0. So you see this position is 0. 0 volt means 0 resistance, right, in this context. And when I open circuit these two terminals, that is Rx is not connected, that is corresponding to Rx is equal to infinity. So the output voltage will be as it is, that is 1.5 volt, which is the supply voltage. And since the voltmeter range itself is 1.5 volt, that will indicate the full scale deflection. Right. And then when I connect this Rx equal to R1, what will be the output voltage? 0.75 volts, half of that, half of the supply voltage. So in the middle, you see here, you will see the deflection at this position corresponding to Rx is equal to R1, right? So if you can calculate on the right hand side, this is Rx is equal to 2R2, so 2R1. This is Rx is equal to 0.5 R1. So as you go away from the center position, then you will see that the scale is getting cramped. Like you see, in this range, all the values are cramped, and in this range, all the higher values are cramped. Right? So only in this range you see that it is slightly linear. Otherwise, it becomes highly nonlinear at both ends of the meter. Right? So one has to choose the R1 properly with some a priori knowledge about Rx. If you have some knowledge about Rx that it will be lying in this range, then accordingly you have to choose one of the resistances in order to bring the deflection close to this into this range, because this is the range where it is linear. Otherwise here it will be very difficult to note down the reading, and probably maybe your recording of the resistance value will be incorrect, right? So it is better to operate in this region. Okay, fine. So you can see it is a simple extension of the previous discussion of electronic voltmeter. We have simply converted the voltmeter into ohm meter by converting the unknown resistance into unknown voltage that is being measured by the voltmeter. Now we can overcome this limitation of non-linearity associated with this circuit with a circuit assisted with by a transistor. Okay, so this has a linear scale. So this is a linear ohm meter. Here, as you can see, you have a supply voltage which is provided as 15 volts, and R1 and R2 are selected such that VR1 is always maintained at 5.7 volts. So this is a PNP transistor. Okay, this is a PNP transistor. So as you can see, this is my emitter, this is base, this is collector, and we know that when the base emitter junction is forward biased, then since it is PNP, this is positive and this is negative. So when this is forward, the transistor will conduct. Okay, so when you maintain this voltage difference as 5.7 volts by appropriate choice of R1 and R2, then then when the transistor is conducting, considering 0.7 volt as the voltage drop, this voltage is like VBE is equal to VRE. So this VR1 is equal to VBE plus VRE. Right, so VRE becomes 5 volts. VRE becomes 5 volts. Now here see that RE consists of two resistances. One is a fixed resistance and one is variable resistance. Right, now you can see that the collector consists of the unknown resistance which is connected here. Okay, now we also utilize the fact here that IC is almost equal to IE, which is true in the case of transistor circuits. Right, now since these resistances are chosen by us and the voltage is maintained at 5 volts here when the transistor is conducting, we know how much IE, the current IE is flowing. Right, so we know, we have the knowledge of IE, accordingly we have the knowledge of IC as well, that is a collector current, and that collector current is flowing through the unknown resistance. So the voltage which is developed here is IC into Rx. IC into Rx. So we use the electronic voltmeter here to measure the current. Right, so sorry, to measure the voltage developed across the unknown resistance. And since this relationship is linear, see, this is known quantity, this is measured quantity, and since this relationship is linear between unknown resistance and the voltmeter for a fixed value of current, then the voltmeter readings will be linear. The voltmeter can be calibrated in a linear manner. So this becomes a linear ohmmeter utilizing voltmeter as the for the measurement of unknown resistance. Right now, by choosing the value of Re appropriately, we can choose the value of current IC. Okay, that's why this is kept as variable resistance. See, this voltmeter range is fixed. That means it can measure only up from 0 to 5 volts, isn't it? So if I choose Re, let's say if I choose Re as 1 kilo ohm, what will be the current flowing through the meter, flowing through the unknown resistance? If I choose Re as 1 kilo ohm, what will be IC? VRE divided by Re, that is 5 divided by 1 kilo ohm, 5 volt, which is 5 milliampere. Okay, 5 milliampere. That much current is flowing through the unknown resistance, but voltmeter can measure only up to 5 volts. That is the range. So Rx max it can measure is 5 divided by 5 milliampere, that is 1 kilo ohm only. Right. So this range becomes 0 to 1 kilo ohm when I choose Re as 1 kilo ohm. So if I vary the Re, then I can change the range. But for all the ranges, the voltmeter will indicate the resistance in the linear manner. So this is a linear ohmmeter circuit. Fine. So we have seen how one can utilize the op-amp based circuit for voltage measurement, and we have also seen that how to overcome the non-linearity associated with ohmmeter. Now this again falls under electronic resistance measurement, because we have utilizing transistor here plus the external power supply. Okay. Now we'll move ahead to discuss about the AC quantity measurement. Till now we were discussing the utilization of op-amp for DC voltage measurement. If you remember our discussion, that extension of PMMC instrument for AC quantity measurement, we utilize the rectifiers. The reason being, PMMC instruments are non-polarized, so the current direction must remain same irrespective of the polarity associated with the input input voltage that is being measured. So the similar approach is taken here, except the fact that we are utilizing op-amp in association with PMMC. So the AC is not directly supplied to PMMC, but it is basically first operated by op-amp and then it is supplied. So in this case, you can see that these different resistances RA, RB and RC are provided to choose the range for E. So different ranges of E1, E2, E3 are obtained with the choice of resistance. That is not an issue. We have already seen that. Once that AC quantity appears at the positive terminal of the op-amp, now which is this configuration? Can you remember? Which is this configuration of op-amp? First tell me what will appear here. So we know that V plus is equal to V minus, right? Equal to V minus. But what is V minus?
V in.
V in. But V minus is connected to V0, right? And V plus is V in. Therefore, V0 is equal to V in. Which is this configuration? We named it some. We gave some name, no, to this. There is some name for this.
Voltage follower.
Yes. So this is voltage follower. Right. So whatever is appearing here, EB will also appear here. EB is the basically peak voltage of the sinusoidal apply as input. So it will appear here. But what is the advantage of voltage follower? What is the purpose if same thing is appearing here? Why can't I directly connect this here? Do you remember? Why did we choose voltage follower device circuit?
Perhaps for current effects,
So
something like that. Perhaps that will affect the current flowing through that or something like that.
current flowing through what?
I mean through the meter or something like that.
Can you be more specific? It's quite vague. Yes.
Avoiding loading effect.
Avoiding loading effect. That means this portion is now separated from the loading effect provided by the meter. Usually the loading effect is provided by the meter. By choosing this configuration, we have isolated these two in one way that this offers very high input impedance. So very less amount of current is drawn from this part, but we need some current to drive the meter, and that is being supplied by the op-amp. Okay, so the ideal output resistance of op-amp is 0, isn't it? And ideal input impedance is infinity. Right? So we use that fact. That's why voltage follower is used. So it is like you can say that it is simply a buffer which is taking input, providing it as it is as the output. Just that these features are provided: high input impedance, low output impedance. Now, if when EB appears here, EB is the peak voltage. Remember, what will be the voltage here after the diode? So the voltage here is like this only, both positive and negative cycle. EB minus EB. And here after diode performs rectification, similar to the way we discussed in the half wave rectifier based voltmeter, the without op-amp, that circuit also we use one diode for rectifying the input. Then only positive cycle will appear here, plus there is an effect of forward voltage drop, that is peak voltage now will be EB minus VF. Okay, negative is clipped off because diode will not conduct in the negative half cycle. So the current flowing through the meter, what will be the current flowing through the meter?
The
How will you
average
calculate?
value of
Average value, that is I average, correct. How much is I average?
0.31 times 0.3185 times
3185 times I peak.
yes sir.
What is I peak?
EB minus VF by RS plus RM.
Right now, if you remember, if you can see that if you forget about this part, the op-amp part, the other calculation are exactly similar to the previous half wave rectifier based voltmeter, isn't it?
Yes sir.
Same calculation, no difference. Just that this is providing the advantage I just mentioned. The issue here is, if you remember our that discussion also, we were always considering VF as 0.7 volts. But if the diode is not silicon based diode, let's say germanium based diode, that this value will change, and with temperature also this will change. In fact, from diode to diode also this will change, right? It may be 0.71 or 0.75, maybe 0.6 also. So in the calculation we are taking this as 0.7, but if in practice this is not 0.7, our entire calibration will go wrong. Am I right?
Yes sir, there will be some error.
There will be some error. How to avoid this error? So if you remember in the transistor based circuit, the differential amplifier which we used for the voltage measurement, there we got rid of this 0.7, no, in case of transistor. How did we get rid of that?
So one NPN and one PNP.
No. They both were NPN that time. But we used another transistor, right, to provide that reference of 0.7 volt, right? Isn't it?
Yes, sir. Yes.
Here even that is not needed. Okay, here that is not needed. Why? Because that extra drop can be taken care.
So you're not audible. So you're not audible.
Am I audible now?
So now all right. So now okay. So now again you're not audible.
Hello,
So now you're audible.
audible. Now I'm audible when the
Yes,
screen
yes,
is
sir.
there.
Now you are.
Okay, thank you. Fine. Okay. Yeah. So one can get rid of this problem associated with the voltage drop across diode, which is variable function of temperature and other facts. The diode make also. One can utilize this simple change where the feedback to the negative terminal is not derived from the output of op amp, but from the cathode terminal of the op amp. Okay. Oh, sorry, diode. So what have we achieved here? That what is the output voltage in this case? Now you see what will be the output array. What will be the output voltage in this? Again, we use the fact that V plus is equal to V minus. V plus is EB minus EB. So what will be the output voltage here? Plus EB and minus EB, right? Am I right or am I
Yes,
wrong?
sir. Yes, sir. Now.
No, it is not correct. Why? It is not correct. So this is wrong. So the voltage here is positive and zero na for negative, because diode has already rectified. But what is the voltage level here? It is EB. You see, EB. Now tell me what is the voltage waveform here at this node? What can be the voltage waveform at this node?
So with peak EB plus 0.7 maybe.
Yes. So this is EB plus VF, and in fact it is not there. Diode is not conducting, right? So the output voltage will take care of the voltage drop across diode, and the feedback mechanism will make sure that whatever EB is there will appear here at the cathode terminal of op-amp. So the supply voltage to the meter is appearing as it is as that of the input without any effect of forward voltage drop, right? But at the same time we have achieved the required rectification. So isn't it advantageous that we have got rid of the effect of diode, the undesirable effect of diode, that is VF, but also at the same time got the rectification operation, and the subsequent calculation exactly remain the same as here, just that this minus VF will not appear now in the calculation. Okay, it will be simply EB by RS plus RM, and by varying this resistance you can calibrate it for the given for the required range of E. Okay, so this is how it is done. Now in both the circuits we had this input capacitance C1 which is being connected. Why is it connected? Can someone tell? If you focus on this part. Why is it connected? What is the purpose?
Maybe so that it is a high pass filter, maybe something like that.
High pass filter for what purpose?
So that low frequencies can be singled out.
Yes. So you see, we are measuring AC quantity, isn't it? So we want to make sure that DC quantities are being filtered out before AC quantity is being measured. Right? So the DC is first filtered out by using this capacitance in series. This is the high pass mechanism, high pass filtering mechanism, and these capacitances C2, C3, C4 are basically utilized to nullify or to compensate the effect of input capacitances associated with op-amp terminals. Now we'll not go into details of that. Probably in the next after few lectures we may probably come to this point, but since you have not studied op-amp, let us not discuss about the differential capacitance and the common mode capacitance associated with op-amp and all. So just for time being, only consider that this is used for filtering of DC quantities in the input. Now the same voltage follower can be further extended to a nonlinear amplifier. Same approach, right? This is again a precision rectifier, but it is basically converting the voltmeter into low level voltmeter. Means if the input supply voltage is of low in magnitude, then one can use the non-inverting configuration. So this is basically non-inverting AC amplifier, you can say, because we have used diode here, of course, for the purpose of rectification. But if the input is positive and negative, that is AC quantity, then output will also be positive and negative. Just that use of diode will basically block the negative half cycle, right? All the calculations remain the same. It is just that what is the output voltage here? Can someone tell? Yeah, it is already given. AV into EP, right? AV is the gain. How much is the gain? One plus R2 by R3. That is the gain. You can set. So if this is in millivolts, if this meter requires 0 to 1 volt, then you can choose the gain accordingly. Okay, right? We have already calculated how to find out the values of this R1 and R2 and R3. Sorry, right? So this is a simple extension of the previous one to measure low level voltages. Now you can appreciate that when the supply is positive and negative both with respect to 0 volts, you see the reference is 0 and the potential is going above and below the reference voltage, and that is why you need both power supplies. Okay, so if you use only one power supply and this, if you let's say ground, then you will not see the negative being magnified, amplified at all or processed at all. Okay, so that's why this is needed. V minus V. Again, in the case of DC also, we have seen that this feedback resistance can be simply replaced by this, where the voltage is being converted into current. Same approach is taken in the case of AC quantity measurement, where AC input is provided at the positive terminal, and in the case of feedback resistance, you put the meter along with a diode in series to block the negative cycle of the output, and we use the same argument that V plus is equal to V minus, and V minus in that case is maintained at peak peak voltage, E peak. So the voltage here, maximum voltage is E peak. So the current flowing through this R3, IR3, is E peak divided by R3, isn't it? And again, this current IB is very much less in comparison to IR3, which is, and IR3 therefore is equal to IM, meter current. So the current flowing through the meter, the peak current, is basically I peak is E peak divided by R3. So we can choose this resistance using this variable resistance by adjusting the zero position and the full scale deflection position, right? So you are basically converting the voltage into current, which is flowing through the meter, and we know that PMMC is a device which is indicating the deflection in function of current. So that is the fact we are utilizing. So this is a voltage to current converter with half wave rectifier. Same calculation will go. So you can expect in your exam some problems related to these designs. Fine. Now till now we were only discussing about half wave. We have also discussed in the previous case about full wave, that we have to utilize 4 diodes in that case for generating the output for both cycles, where both cycles are positive in that case, and the same argument. So you see here in this place, in this case it was half wave rectifier, here it is full wave rectifier, right? So in the positive half cycle, when this is positive, the current will flow like this, and in the negative half cycle the current will flow, because it will come from here into the op amp. So op amp is also sourcing the current and it is also sinking the current, okay? Because in the positive cycle, this node, the output of the op amp, is at higher potential in comparison to the common terminal. That's why these diodes are forward biased. Whereas in the negative cycle is at lower potential than the common terminal, so the current direction will change. Well, but the current direction will remain the same for your meter. Current direction will not change for the meter. But how much is the current flowing? Who is deciding how much is the current flowing? It is being decided by this. So E peak is appearing here, also here. So IM is basically equal to E peak divided by R3 only. Okay, it is not even dependent on RM. You see, it is not even dependent on RM. It is basically decided by R3 only and the supply voltage input. Now let's say we are given a meter whose full scale deflection current is 1 milliampere, right? And the meter resistance is 1 kilo ohm, and if the VFSD, full scale deflection voltage, is given as 100 millivolts, we are asked to calculate what is R3. Okay, what should be the value of R3? Now can someone tell how can I calculate R3? For R3, what I need? IFSD is already given. IFSD is E peak divided by R3. So R3 is E peak divided by IFSD. Is it correct? Can someone quickly tell? Do you remember our discussion on calculation of component values in the case
So
of half and
perhaps
full?
IFST is something like average value, I think.
No.
Related to
Yeah, you tell me IFSD correspond to what? I
full scale deflection.
average. A full scale deflection, which is nothing but I average of for AC quantities, right? But
Yes,
when
sir.
we calculate the values, which quantities we used?
So we used a peak.
Peak, right? So what is I peak in the case of full wave rectifier? I average divided by,
0.637.
right? Now I average is given maximum
1
1 milliampere. So I peak is how much?
1.57 milliampere.
57 milliampere, right? Then what is V peak?
1.57 volt.
1.57
Volt.
volt.
RM is 1 kilo ohm.
Yeah. So
1.57.
no, I'm asking what, sorry, I used a different variable. I should use what is E peak? What is E peak? Huh? You tell me what
VP
what value?
minus
Huh? Huh?
VP
What is
minus
VFS?
this diode voltage.
No, forget about diode, because the diode voltage will not appear in the calculation, right? Here,
Yes.
did it appear? No.
No. It won't
So
appear.
what is V peak? E peak.
So here VFSD is in RMS, I think.
Yeah, it must be in RMS. What I told you, when it is not mentioned, you should always take it as
RMS.
RMS. So what is E peak then? VFSD into?
So nearly 141.4 millivolt. 141.4 millivolt.
4 millivolts, right? So this is the peak voltage. This is the peak current through the meter, and the same current is flowing through R3. So what is R3? E peak divided by I peak. So what is that value?
So nearly 90 ohm.
90 ohms. So you have to connect R3 90 ohms. What we have achieved? We have achieved 0 to 100 millivolt VRMS measurement in terms of 0 to 1 milliampere DC current, right? Because PMFC is DC, no? So we have converted this voltage measurement to current measurement, you see, with voltage AC into DC quantity, that to voltage to current, by using op-amp based full wave rectification, right? So this is the calculation are exactly the same like previous one, just that the diode effects are not taken into consideration. Fine. Okay. So this is more practical in comparison to the previous circuit which we discussed. Fine. So a similar approach can be now taken for current measurement. Okay. So now we are interested to measure I, that is current. So in most of the current measurement circuit, okay, the current is basically converted into voltage first, and that voltage is measured using voltmeter. So this is one of the configuration which is given where the this is suitable for low current measurement. So what is done here is that you connect a series resistance RS in the circuit through which you want to measure the current in. Okay, So let's say there is a circuit, and in this branch of the circuit we want to measure the current in this. So you put a small, very low value resistance in series so that it is not going to affect the circuit. So this is a very low value, RS is low value resistance, and when the current which is being measured, IS, flows through this resistance, it will develop some voltage, and this Vs is RS into IS, which is developed, and that is measured by the voltmeter. Okay, so this now we are discussing about AC, the DC quantity. So if you go, this arrangement is used here. You see, same arrangement is used here for current measurement, but current is now measured in terms of voltage. So it is interesting to see current is first converted into voltage, and here voltage is again converted into current. All right, current corresponding to the one which is flowing through the meter. Okay, fine. So this is current measurement using electronic instrument by putting a series resistance putting a resistance in series with the circuit through which the current is being measured. Right now, we have another approaches also for current measurement, but the case is that till now we were discussing about the voltage measurement, current measurement, AC and DC. The ranges are quite small. Okay, quite small means let's say 0 to 10, 0 to 20, or 0 to 25 volts, or 0 to 50 volts. Even 50 volts is too high, right? So in that case, when you use these meters for measurement of very high voltages, then they are provided with probes, different probes, like high voltage probe, high current probe, or Hall effect based probe. So this is the probe you probably will see. I hope you will now see once you come back. Once you probably, I won't say come back, but maybe you are coming for the first time in the campus. So when our lab will start physically, then you will get to see these probes. Okay, so these probes internally have the voltage division mechanism, where this voltage being measured, which is very high value, is brought down by this voltage division, and that voltage is being measured by the meter, and this decreasing voltage from high value to low value can occur at the scale of thousands or hundreds of thousands. Okay, so for example, let's say this meter is designed for 0 to 10 volts. If you want to utilize it, and if the probe which is used, which is capable of bringing down the voltage 1000 times, so you can actually measure it for the range of 0 to 10 kilovolts. Okay, it is possible because this voltage division is performed by meter, so the performed by the probe, and the meter will not get affected. Anyway, it will get 0 to 10 volt only. Okay, so from 0, so you can, since the voltage division and the relationship is linear, you can simply calibrate the instrument or convert it by the factor of 1000. Okay, it is as simple as that. Similarly, you have high current probes, where in the circuit where very high amount of current is flowing, then one can utilize these current probe, which are nothing but the current transformers. Okay, so you can see this is a current transformer. So do you remember what is the relationship between the primary current? So this is my primary current, this is my secondary current, and the relationship between primary and secondary current with the number of turns in primary and secondary. How are they related?
IS is equal to NS by NP.
NS by NP. You see, then in this case, NP is how many turns are there in the primary? This is a single turn. You see, single wire is there, no? So you consider it as a single turn. So NP is 1. Okay, and you see NS is not 1. It is, there are a number of turns here. So NS is greater than NP. So IS will be much less than IP. Okay, so that division, the current level is brought down by the current transformer, and that is being measured by the current meter, by the our meter, normal meter. Okay, so you see these different probes, different terminals are provided for voltage measurement and current measurement, and this C represents the common terminal, which we already discussed, right? Common terminal. The usually such clips are there. You can clip this around the wire through which you want to measure the current in. Okay. Similar approach is also now this I just brought because this topic came, but Hall effect. What is the principle of Hall effect? We'll discuss later on when we start discussing about sensors in the second half of this course. But for the time being, understand that there is a material which is capable of converting, providing the voltage corresponding to current flowing through. So you can see that it is a simple sheet, or this is a Hall sensor. Through that, when you pass the current, it is a current conducting material, pass the current, and when you subject it to external magnetic field, then on the opposite side of this device, a voltage is generated which is proportional to the current, of course, and the magnetic field. When you fix the magnetic field, then the voltage being generated becomes proportional to current. Okay, so these Hall effect sensors are also look like the current transformer, but the working principle is different than current transformer. They are basically slightly less bulkier than current transformer, but the purpose is to convert the current into corresponding voltage. So this is known as Hall effect. We'll discuss the equations later on, but this for the purpose of demonstration, I just said that the voltage is proportional to current I when the Hall effect sensor is passing the current and it is kept in the external magnetic field. Fine. So these are the kind of probes which we'll use to convert the higher level into lower values. Right. So so we'll now start the discussion on next topic from next class. Okay, fine. Thank you.
Thank you, sir.